So, good morning dear students, welcome back to module 5 of fluid properties. So, module 5 is nothing but the continuation of module 4 in which we worked out 4 numerical problems involving Newton's law of viscosity, and in continuation of that we will be working out a few more application problems on viscosity in this module. So, which will be highly useful for answering questions in competitive examinations like GATE, Indian Engineering Service, Indian Civil Service, etc. So, let us now go to the first slide of this module. So, let me read out the problem statement. A hydraulic lift consists of a 50 centimeter diameter ram and slides in a cylinder of diameter 50.015 centimeters, while the annular space is filled with oil having kinematic viscosity of 0.025 centimeters square per second and specific gravity of 0.85. If the rate of travel of the ram is 9.15 meter per minute, find the frictional resistance when 3.85 meters of ram is engaged in cylinder. So, let us present the schematic diagram. So, the outer cylinder, which is marked in red lines, has a diameter of 50.015 centimeters, and the moving cylinder, which is called the ram, that is marked in blue, dark blue color, which in fact can move up and down inside the outer cylinder. It has got a diameter of 50 centimeters. So, the diameter of the outer cylinder in which the ram is moving up and down or reciprocating. Now, the annular gap between the outer cylinder and the ram is filled with a lubricant for ease of movement of the ram inside the cylinder, with an oil having kinematic viscosity. So, the kinematic viscosity of oil is given, that is 0.025 centimeters square per second, and also the specific gravity of the oil is given, which is 0.85. Now, the rate of travel of the ram, that is the velocity of the ram which is moving up and down inside the outer cylinder, is given as 9.15 meters per minute, and you are asked to find out the frictional resistance, that is the shear force that comes into play when the ram is moving inside the outer cylinder up and down. When 3.85 meters of ram is engaged in the cylinder. See, when it is moving up and down, the shear force varies depending upon the area of, the shear stress varies depending upon the area of contact of the ram with the cylinder. So, the area of contact varies with time. So, sometimes it is minimal and sometimes it is maximum. Now, let us first list the data with proper notations, what is given in the statement of the problem. The diameter of the cylinder, that is capital D, we will use, that is the outer cylinder, that is 50.015 centimeter. So, let us all convert everything into SI system. So, if length is given, it should be in meters, and if the time should be in seconds, and the force should be in newtons, and the mass in kilogram mass. So, 50.015 centimeter we express in meters as 0.50015 meter, because 100 centimeters make 1 meter. So, divide this by 100, you will get the quantity expressed in meters. Then the diameter of the ram, I am using small d because the diameter of the ram is smaller than the diameter of the outer cylinder. it is 50 centimeters, that is 0.5 meter. Then the kinematic viscosity of oil is given, that is nu, which is given in centimeter square per second, 0.025 centimeter square per second, that is 0.025 strokes, that is 1 centimeter square per second is 1 stroke. Now let us express it in meter square per second. So 1 centimeter square is 10 power minus 4 meter square. So 0.025 multiplied by 10 power minus 4 meter square per second. Now specific gravity of oil is given 0.85. Then rate of travel of ram, that is the velocity of the ram, that is to and fro movement. So it goes up, then goes down, goes up, goes down in the same rate. That is the linear velocity is 9.15 meters per minute. So let us express it in seconds. So 1 minute is 60 seconds. So 9.15 meters divided by 60 seconds, you get 0.1525 meters per second. Then the length of ram engaged in the cylinder. So at the particular instant, the length of ram in contact with oil or in contact with the cylinder is 3.85 meters, that is capital L. So we are asked to find out what is the frictional resistance, that is the shear force, which comes because of the viscosity of oil that is occupying the annular space, that is a gap between the outer periphery of the ram and the inner periphery of the outer cylinder in which the ram moves up and down, that we call it as F suffix V. So F standing for the shear force and V standing for the viscous nature of the force. Now again, so now these two are parallel plates, the outer ram, the outer cylinder and the inner ram, right. So if I have a cut section, if I cut this in this fashion, cut here and then look from the top, so it will be like this, it will be like this. So this is the sectional view, that is a plan, and this is the sectional elevation. So here this is D and this is capital D. So capital D we know, small d we know. Now this distance, that is the annular gap between, let this be y, this is y. So we have D is equal to D plus 2y. This is small d, this is capital D, and this gap is the thickness of the lubricant, So capital D is equal to small d plus 2y. So d we know, small d we know, therefore y you can find out. So y is equal to d minus d divided by 2. So this is what I have put. So thickness of the annular space between the outer cylinder and the inner ram is d minus d by 2, which comes to 0.000075 meter. Okay. Then again we use the Newton's law of viscosity, that is tau is equal to mu multiplied by dV over dy. So tau is the shear stress that comes into play, mu is the viscosity of the lubricant, viscosity of oil, for which the kinematic viscosity is given. Let us find out the viscosity using the relationship between viscosity and kinematic viscosity. Then dV over dy is the velocity gradient or the rate of angular deformation of the fluid. So shear stress, where at the outer peripheral surface of the ram in contact with oil in the annular space between the ram and the outer cylinder. So this is so I have given elaborate explanation to understand where the shear stress comes into play. So shear stress acting at the outer peripheral surface of the ram, which is in contact with the oil, which is filling the annular space between the ram and the outer cylinder. So we know that tau is equal to the shear force divided by the area over which the shear force acts. So this is what actually is required. Now let us find out the area of contact. Now say this length, that is this length is which is given in dotted lines. I say this is the length of the ram which is in contact with this cylinder, outer cylinder, that is 3.85 meters. Now when 3.85 meters is in contact, what is the area? That is, I want this that is the circumference, right, circumference of the ram multiplied by the length, that is 3.85 meters. That is, I want this length, say this is L, that is 3.85 meters, and this diameter is D, and I want the circumference. The circumference multiplied by the length will give you the outer peripheral surface of the ram which is in contact with the oil. So that will be circumference of ram, which is pi d, and length of the ram in contact with the outer cylinder, that is L, pi dl. So you get the area of contact. So this shear stress due to viscosity of oil is distributed over this area, 6.0476 meters square. Now let us determine the viscosity of oil. Now kinematic viscosity is given. Mass density of oil is nothing but specific gravity of oil multiplied by mass density of water. So 0.85 multiplied by 1000 kilogram mass per meter cube, you get 850 kilogram mass per meter cube. Then now what is mu? We know that kinematic viscosity is equal to mu divided by rho. So nu is known, mass density we have just determined using the specific gravity, therefore you can find out mu. So mu is equal to nu multiplied by rho. So 0.025 into 10 power minus 4 meter square per second multiplied by 850 kilogram mass per meter cube, you get 0.002125 Newton second per meter square is the viscosity of the lubricant. Now we have the Newton's law of viscosity as tau is equal to mu into dV over dy. So as the annular space y is very small, we assume the velocity gradient to be linear. That means dV over dy can be replaced by v by y, where v is the velocity of travel of ram, which is 0.1525 meters per second, and the distance, that is the thickness of the annular space, is this much, measured from the inner wall of the outer cylinder. Therefore, you can find out the velocity gradient simply as the ratio between the velocity of travel of the ram and the thickness of the annular space. So you get 2033.33 per second. So now tau is equal to, tau is nothing but the viscous force divided by area is equal to mu multiplied by v by y. So mu we know, v over y we know, and a we have determined, therefore you can find out Fv. So Fv we get ultimately as 26.13 Newton. So Fv divided by the area of contact when the length of contact of the ram with the outer cylinder or lubricant is 3.85 meters, and the viscosity of our lubricant, and then the velocity gradient. I hope you have understood the solution of this problem. We will go to the next problem, example 8. So determine the torque and power required to run a 15 centimeter long and 5 centimeter diameter shaft running at the rate of 500 rpm in a 5.1 centimeter diameter concentric bearing flooded with oil of dynamic viscosity 100 centipoise. So let us translate this statement into a schematic problem. So you have a shaft, an inner shaft, which is revolving inside an outer concentric bearing. Okay. So this is the inner bearing, or sorry, the inner shaft. Which is rotating. It is rotating. It is rotating inside an outer bearing. The diameter of the inner shaft as well as the diameter of the outer bearing are given. The diameter of the outer bearing is 5.1 centimeter, capital D. The diameter of the inner bearing is, inner shaft is 5 centimeters. And the annular gap, the annular space between the outer bearing and the inner shaft is filled with oil. So this is the cross-sectional view. That is, you are cutting here and then you are looking for the top. This is the view we get. So let the velocity, linear velocity, that is because of the rotation of the shaft at the outer periphery of the shaft, let it be small v, and the thickness of the lubricant, that is the annular space, be y, and omega is the angular velocity of the shaft. So v is the linear velocity. So we can relate the angular velocity and the linear velocity as v is equal to r omega. V is the linear velocity, that is in meters per second. R is the radius of shaft in meters. Omega is the angular velocity, that is in radians per second. So length of the shaft, we use the notation L, 15 centimeters, put it in meters, 0.15 meter. Diameter of the shaft, that is the inner shaft, which rotates inside the outer bearing, that is small d is 5 centimeters, put it in meters, 0.05 meter. The rotational speed of the shaft, that is 500 rpm. So we should also know the relation between the angular velocity and rotational speed, that is angular velocity omega is equal to two pi n by 60. 2 pi n by 60. So omega will be expressed in radians per second. So 2 pi, if the shaft makes one revolution, that means it covers 360 degrees, or 2 pi radians. 2 pi radians. So one revolution corresponds to 360 degrees or 2 pi radians. So n is the speed in rpm. So in 1 second, the number of revolutions made will be n by 60. So n is in rpm. So if I want the number of revolutions per second, it is n by 60 revolutions per second. So one revolution corresponds to 2 pi radians. So n by 60 revolutions correspond to 2 pi n by 60. So this is the angular velocity in radians per second. Now the diameter of the concentric bearing inside which the shaft revolves, that is d is equal to 5.1 centimeter, slightly bigger than the diameter of the shaft. Then viscosity of oil is given in centipoise, that is 100 centipoise. We know that 1 poise is 0.1 Newton second per meter square. So 1 centipoise will be 0.1 into 10 power minus 2 0.1 sorry, 1 centipoise is 1/100th of a poise. 1/100th of a poise. So 100 into 10 power minus 2 poise, that will be 1 poise. Again, 1 poise will be 0.1 Newton second per meter square. Then what is required is the torque required for revolving the shaft, that is capital T, power required for revolving the shaft, that is capital P. These two are the quantities to be determined. So angular velocity of the shaft, it is 2 pi n by 60. So n is given, so we get the angular velocity in radians per second as 52.39. Then the circumferential velocity or peripheral velocity or the linear velocity or the velocity of shaft tangential to its circumference, that is this one. V is equal to r omega. Okay. So radius of the shaft will determine d by 2. Okay. Then peripheral velocity of the shaft, B is equal to r omega, r is 0.025 meter multiplied by omega, that is the angular velocity of shaft, 52.39 radians per second. We get the peripheral velocity as 1.31 meters per second. And the annular gap, the thickness of the annular gap between the shaft and the bearing, that is as we determined in the previous problem, capital D minus small d, that is the difference between the diameter of the outer bearing and the diameter of the inner shaft, the whole divided by 2. That will give you the thickness of annular gap. That is this one. Say this is your shaft, this is your bearing, this diameter is d, this is small d, so I want, this is y, this is y. So you have d is equal to d plus 2y, therefore y is equal to d minus d by 2, as same as we discussed in the previous problem. So that is also determined. Now again we go back to the Newton's law of viscosity, tau is equal to mu multiplied by dv over dy. Now as the thickness of the annular gap between the shaft and the bearing is very small, so we assume the velocity gradient to be linear, hence the term dv over dy is replaced by the term b over y. So v is the linear velocity of the shaft rotating inside the concentric bearing. Y is the thickness of the annular gap between the shaft and the bearing. So tau is equal to mu multiplied by v over y. So tau, mu we have just determined, or so it is given in centipoise, and centipoise we have expressed in the fundamental SI units, that is Newton second per meter square. Then the velocity, linear velocity we have determined 1.31 meters per second. So the speed is given, the rotational speed, find out the angular velocity and then the linear velocity. Then y, that is the thickness of the annular gap, that is 0.0005 meters. This one, this is y. So we get the shear stress exerted on the peripheral surface of the rotating shaft in contact with oil filled in the annular gap between the shaft and the concentric bearing. Now, what is the area over which this shear stress is distributed? That is area A. So here it is again the circumference of the shaft, which is rotating inside the outer bearing, multiplied by the length of the shaft in contact with the oil. So the length of the shaft in contact with the oil is given in the problem statement as 15 centimeter long. So it is 15 centimeter long. So 2 pi r is the circumference. So 2 pi, radius multiplied by the length, we get 0.02356 meter square. So the peripheral force on this area, so how the force acts, here so suppose if it is rotating, so the force acts in this direction. This is the direction of F. In the direction of the linear velocity. So tau is equal to F over A. Tau we have just now determined using Newton's law of viscosity. Area we have determined, so therefore you can find out F. F is equal to tau multiplied by A. So this is uptime. So what is the torque? Torque is, so this force acts, so in fact the shaft is rotating inside the bearing. So the torque that is created will be T is equal to F multiplied by the radius of the shaft, the peripheral force. F is the circumferential force or the peripheral force, which is created due to the viscosity of the lubricant or the oil which is filling the gap between the inner shaft and the outer bearing. So peripheral force, which we have just determined using Newton's law of viscosity, multiplied by radius of shaft, we get 0.154 Newton meter. So F is in Newton, radius in meters, therefore Newton meter. Then what is the power required? The power required will be torque multiplied by angular velocity. So torque in Newton meter we have just determined. The angular velocity we have already determined, 52.39 radians per second. We get the power required in watts. So watts is the SI unit for power. So again I summarize the solution for this problem. So what is required is, you are required to find out the torque and power for the shaft to rotate inside a bearing, and the gap is filled with oil of the given viscosity. So here you find out the shear stress using Newton's law of viscosity, then the shear force because of this shear stress, and the torque required for this peripheral force, and also the power required for this torque. Now let us take the next problem. A tape of 0.015 centimeter thick and 1 centimeter wide, so that is say a tape, the width is 1 centimeter and the thickness, that is this thickness is 0.015 centimeter, is to be drawn through a gap, with a clearance of 0.01 centimeter on each side. A lubricant of dynamic viscosity 0.021 Newton second per meter square completely fills the gap for a length of 80 centimeters along the tape. If the tape can withstand a maximum tensile force of 7.5 newtons, calculate the maximum speed with which it can be drawn through the gap. So let us put it in a schematic diagram. So this is the tape thickness. The tape thickness is 0.015 centimeter and the width perpendicular to the plane of the paper is 1 centimeter. So the thickness and the width perpendicular to the plane of the paper. In fact, when you have this view, when you look from the top, so you will see only the width, that is 1 centimeter. This is the sectional elevation which has been presented in the figure. This is the top view. So, top view of the tape, you see the width of the tape, you will not see the thickness. The thickness you will see only when you have the elevation. So, this is the sectional elevation. So, this tape has to be drawn through a gap with a clearance of 0.01 centimeter on each side. So, it has to be drawn through a gap. You have to pull the tape, applying a force, that is a shear force. Say the shear force is applied here in this direction. It has been drawn through this gap, and what is the gap on each side, on either side of the tape? So, here this is 0.01 centimeter, and similarly this is 0.01 centimeter. The length which is under consideration of the tape is 80 centimeters, and the gap on the top as well as the gap on the bottom is filled with a lubricant of dynamic viscosity 0.021 Newton second per meter square, and the tape can withstand a maximum tensile force of 7.5 newtons. So, the shear force that can be subjected to is only limited to a maximum of 7.5 newtons. So, you are asked to calculate the maximum speed at which the tape can be drawn through the gap. Okay. So, the clearance on each side, there is dy, it is given as dy, this is given as dy, this is dy, is 0.01 centimeter, put it in meters. So, multiply by 10 power minus 2. Dynamic viscosity of oil is given. Width of tape perpendicular to the plane of the paper. So, this is the paper, the diagram. Perpendicular to the plane of the paper is 1 centimeter. That is, when you have the plan view, what you see is the width of the tape, that is 1 centimeter. Put it in meters. Then length of the tape in contact with the oil is given. So, as the gap is completely filled with the lubricant, both the bottom and top faces of the tape are in contact with lubricant. So, you have a shear force on the top as well as at the bottom. So, contact area will be the top surface, that is width of the tape multiplied by the length of the tape in contact with lubricant. So, width of the tape is B, this is L, 0.01 into 0.8. And both the top face as well as the bottom face of the tape is in contact with oil, therefore, you multiply by 2. This is the contact area, total contact area, total contact area. So, maximum tension the tape can withstand is 7.5 newtons. So, this is the maximum shear force acting on both the bottom and top faces of the tape together. Therefore, maximum shear stress is F max, that is 7.5 by 0.016 meter square. So, you get 468.75 Newton per meter square. Then again, as per Newton's law of viscosity, this is tau max, because we derive this from the maximum shear force, that is 7.5 newtons, and mu is given. So, we can find out and dy is this much, 0.01 centimeter, 0.001 meter. So, you get dV, dV is 2.23 meters per second. So, maximum speed with which the tape can be drawn through the gap is this much, that is assuming the velocity gradient to be linear, that is dV by dy is equal to V by y. So, dV can be replaced by V, that is 2.23 meters per second. So, maximum speed with which the tape can be drawn through the gap is 2.23 meters per second. So, today we have worked out totally 3 problems, and hope you have understood all these. And we will in the next sitting we will have module 6, wherein I will tell about vapor pressure and then compressibility of fluid. So, with this, thank you very much for the patient listening and wish you a good day. Thank you.